Hi, this is OCR Gateway Physics Revision for section P1 Microwaves. In this section we'll be looking at cooking and mobile phones, two applications of microwaves. So we're going to compare a conventional oven to a microwave oven. A conventional oven uses infrared radiation or heat. It works by heating the surface of the food, and then that heat energy is passed to the centre of the food by conduction, if it's a solid, as in this picture here, or by convection, if you're heating a liquid. Infrared radiation, or radiated heat, is reflected by shiny surfaces, such as baking trays or aluminium foil. Microwave ovens do not rely on heat or infrared radiation to work. So if you took the temperature inside a microwave oven when it was switched on, you should find that it's just the same as the air temperature outside the microwave. Microwaves can penetrate further than infrared, so whereas infrared or radiated heat only heats the surface of the food, microwaves can penetrate just beneath the surface, so about 1 centimetre into the food. Microwaves, just like infrared, are also reflected by shiny metal surfaces. Just like infrared, they can cause burns when absorbed by body tissue. Microwaves pass through glass and plastic, so glass and plastics are not actually heated by microwaves. If you use a Pyrex dish inside the microwave and it comes out hot, it's because it's been heated by the food, not by the microwaves themselves. Okay, so I mentioned before that infrared or conventional ovens work by using infrared or heat, radiated heat, and that the infrared is absorbed by particles on the surface of the food. Now that increases their kinetic energy, so the particles absorb the infrared waves, they start to vibrate, they heat up. The rest of the food heats up by conduction or convection. In a solid like this, that kinetic energy is passed from or transferred from the particles on the outside of the food to the particles towards the centre. And gradually enough kinetic energy will be transferred so that the particles in the centre of the food also become hot. Microwaves work in a slightly different manner. Microwaves are actually absorbed by water or fat particles in a food. So I'll just underline those. Water and fat particles. So in the outer layer of the food or drink, so about 1 centimetre layer on the surface, any water or fat particles in that layer absorb the microwaves. Now when they absorb a microwave, their kinetic energy increases, so they will start vibrating. Now following that, once those outer layers have heated up, the way that the middle of the food or drink heats up is exactly the same in a microwave oven as it is for a conventional oven. The kinetic energy is transferred to the centre of the food or drink by conduction for food, for solid, or convection for a liquid. So we've talked about microwaves and their use in microwave ovens and cooking. Now we're going to look at microwaves and how they're used in communications, and namely in mobile phones. Mobile phones send and receive information using microwaves, and we're going to have a look at some of the things that can affect a mobile phone signal. So I've got some pictures here at the top of poor weather and surface water, lake. Now both of those things will scatter signals. We can think of scattering as a signal being bounced off in the wrong direction. So if the microwaves are bounced off in the wrong direction, then less of the signal gets to where it needs to be going. That means the received signal is weaker and is of a poorer quality. Another problem with sending any microwave signal or even radio signal over long distances is the fact that the Earth is round. If you want to send a signal over a certain distance, the curvature of the Earth actually gets in the way. There are a few ways around this, which we'll take a look at later. Another problem with microwaves is that they do not diffract very well. Now, if you remember, diffraction means waves spreading out as they pass through a gap. So let's take a look at this top diagram. Now, in this example, we're sending radio waves. So we've got a radio transmitter over here. This could be sending TV signals or radio signals. And we can see the radio wave diffracting as it travels from the transmitter. So the wave is spreading out as soon as it leaves the transmitter. And now, as the waves reach a hill, the hill blocks some of those waves, so not all of them can be transmitted to the other side. But what happens is, once around the hill, the radio waves again start diffracting and spreading out. So even though the hill is in the way, and the hill is higher than this house over here, and it's actually between the transmitter and the house, because of the diffraction of radio waves, the house can actually still receive the signal that's being transmitted from over here, because the radio waves, once past the hill, are diffracting and spreading out so that they reach the aerial on top of the house. So that house would still receive a TV signal. Microwaves do not diffract as well as radio waves. So in this bottom example here, we can see a transmitter again, but this time transmitting microwaves. Microwaves are a higher frequency than radio waves, so a shorter wavelength. And if you remember, the greater the difference between the wavelength and the gap size, the less diffraction occurs. So microwaves have a shorter wavelength compared to the size of the gap, which is why they don't diffract as well as radio waves, which are a longer wavelength. So we can see in this bottom example, because the hill is between the line of sight, the straight line between the transmitter and the receiver, this building here won't receive a microwave signal. Phone signals can also be affected by interference. So if there are two transmitters in the same area that are transmitting on the same or on a similar frequency, then the signal from each will interfere with each other and you'll get a loss of signal. This is also true for radio waves. So what can be done to reduce signal loss? Well, you probably have noticed that mobile phone transmitters are always positioned high up on a mast or on top of a building. This helps to ensure that there is a clear line of sight between the transmitter and the receiver, which is getting around the problem of the fact that microwaves don't diffract. The distance between transmitters is limited, so that means that the signal doesn't have to travel as far and can't degrade as much. And also nearby transmitters use different frequencies. That's so that the signals don't interfere with one another. You may have heard that there are some concerns about potential dangers of microwaves and their use in mobile phones and mobile phone masts. It's thought that if the water inside our bodies absorbs the microwaves, it could heat up, just like the way that water heats up inside a microwave oven when microwaves are used for cooking. And then following on from that, if this does occur, then it's possible that that could cause cancer and tumours. Now, this is actually quite a grey area of science. There's no conclusive evidence that either disproves it or fully proves that this could happen in humans. Actually, the frequencies used in mobile phones and communication are slightly different to those used inside a microwave oven. And also, they're a much lower power, much lower intensity. Of particular concern are children, because their brains are still growing and developing. People who live near mobile phone masts, because they could actually be receiving a much greater intensity of microwaves. And perhaps all mobile phone users could be considered at risk. If we're having long phone conversations, holding our phones close to our heads for a large amount of time, then those microwaves could possibly be affecting our brains. And that's all for P1E.